Caloric restriction, defined as a sustained reduction in calorie intake without malnutrition, has consistently emerged in animal studies as one of the most powerful non-genetic interventions to extend lifespan and delay the onset of age-related diseases, including cancer. A key mediator of this effect appears to be autophagy. By enhancing this cellular self-repair mechanism, caloric restriction improves metabolic efficiency, reduces the accumulation of cellular damage, and helps maintain tissue function over time. When calorie intake is reduced, nutrient-sensing pathways such as mTOR, mechanistic target of rapamycin, are downregulated, while energy-sensing pathways like AMPK, AMP-activated protein kinase, and sirtuins are upregulated. This shift in cellular signaling promotes autophagy, a state in which cells recycle damaged components to maintain internal balance. Under caloric restriction, autophagy is not simply a stress response but an adaptive program that conserves energy, protects cells, and sustains longevity by cleaning up molecular debris before it can become harmful. This effect is especially critical as organisms age, since autophagy naturally declines with age, allowing damaged proteins and dysfunctional mitochondria to accumulate, which contributes to cellular senescence and chronic inflammation. In numerous animal models, from yeast to rodents and primates, caloric restriction has been shown to reduce cancer incidence and delay tumor onset. Autophagy likely plays a significant role in this protection by limiting DNA damage, stabilizing the genome, and preventing the cellular environment from becoming permissive to tumor formation. By clearing out faulty mitochondria and reducing oxidative stress, autophagy helps preserve the integrity of cells and prevents the kind of metabolic reprogramming that cancer cells exploit. Furthermore, caloric restriction lowers circulating insulin and IGF-1 levels, hormones that promote cell proliferation and are often elevated in cancer-prone states. These systemic effects create an environment less conducive to cancer growth, both by limiting fuel availability and by enhancing the body's internal repair systems. Yet despite these benefits, applying caloric restriction as a therapeutic or preventive strategy in humans raises important concerns. Sustained calorie reduction may not be practical or safe for all individuals, particularly the elderly or those with certain chronic conditions. In cancer patients, caloric restriction must be approached with caution, as nutritional deficits can impair immune function, weaken response to therapy, and promote muscle wasting. Moreover, while caloric restriction might delay the onset of cancer, it is not necessarily beneficial once cancer is already established. In fact, in certain tumors that are highly dependent on autophagy for survival under metabolic stress, caloric restriction might inadvertently support tumor persistence unless combined with therapies that block autophagy or cut off compensatory nutrient pathways. Another challenge lies in the translation of findings from animal models to humans, whose biology and environments are vastly more complex. While the underlying molecular pathways are conserved, the extent to which caloric restriction can meaningfully extend human lifespan or reduce cancer incidence without unintended consequences remains uncertain. Some studies suggest that intermittent fasting or time-restricted eating might offer many of the same autophagy-related benefits without the long-term adherence challenges or risks of continuous calorie restriction. These approaches may help stimulate periodic autophagic cycles that mimic evolutionary patterns of feast and famine, promoting cellular renewal while maintaining nutritional adequacy. Research into caloric restriction mimetics, compounds that mimic the effects of calorie restriction without actual food reduction, is also underway. Agents like rapamycin, resveratrol, spermidine, and NAD+ boosters aim to activate autophagy-related pathways while minimizing the need for dietary sacrifice. Although promising, these compounds still require rigorous testing to ensure they do not activate autophagy in ways that may support tumor survival in high-risk individuals or established cancers. Ultimately, caloric restriction highlights a profound biological truth: that the body has mechanisms capable of profound self-preservation when faced with moderate, controlled stress. Autophagy is at the center of this adaptive response, linking nutrient availability to cellular resilience and, in turn, to longer and healthier life. But just as autophagy must be carefully regulated within cells, efforts to harness caloric restriction must be personalized, context-dependent, and cautious, especially when cancer risk is part of the equation. What works in prevention may not always work in treatment, and what slows aging in a healthy body may feed disease in one already compromised.